Okay, so we, after building the background on the quantum circuit model, we come to finally quantum algorithms. So, if let's say we have to divide this course, we have covered the basics of quantum mechanics, then we took a detour and we did quantum metrology. We also touched upon geometry of a qubit. Uh, so look at the homework 4, that has more problems on that. Uh, we covered the quantum circuit model and identities, circuit identities. Now we are coming to quantum algorithms, which would be, part of the quantum computation. And we'll keep back and forth going between these guys, quantum computation and quantum information. So for the next few lectures, we'll be focusing on quantum algorithms, and then we'll again come use the quantum circuit model for things like quantum teleportation, and we'll study also. Uh, we covered the basic aspects of quantum mechanics, but uh, we'll also look at some very deep questions or foundations of quantum mechanics and what can quantum information theory teach us about them. So, in light of quantum information theory. Okay, so let's say, so we'll straight away jump into quantum algorithms now. And we start with a uh, quantum algorithm given by Deutsch, David Deutsch, Deutsch's algorithm. And the problem is the following. Let's say I give you a binary function. So a binary function fx, that means it takes input 0 to 1 and gives output 0 or 1. So given a binary function and I have been given a promise. The promise is it's either a constant function or it's a balanced function. So if f0 is 0, f1 has to be 1. If f0 is 1, f1 has to be 0. So this is the promise. So imagine we are playing a game and I tell you that, okay, uh, you have to tell me whether the function is a constant or is it a balanced function. So the task is to find if fx is constant or it is balanced. By the way, doing basics of quantum mechanics, we also did some quantum cryptography. Remember the uncertainty principle and what happens to the interference fringes when we are observing the electrons going through the double slit. So coming back to the task, uh, this was the Deutsche's algorithm. We have a function, a binary function, and I give you a promise. Either the function is a constant or it is balanced. The task is to find uh, whether it's a constant function or a balanced function. So I have the function, you have to find it. So what do we do on a classical computer? We ask the computer, we put in values. So we need to ask a classical computer, uh, how many times should I ask? If I have a function fx, I'll have an f0, I'll have an f1. Well, I'll have to ask it two times, right? I'll have to ask classical computer twice. Only then I'll be sure. Uh, and then I'll have to compute both values. And I'll answer my question. Either the function is a constant function or it's a balanced function. Uh, Now the question is, can quantum mechanics do better? So for that, consider the following operator, the unitary operator U of f, which is takes an input xy, where xy would be 0 or 1. These are 2 qubits, and it gives me x and a binary addition of f of x. So that's a unitary operator I'm going to be operating on. I'll be interested in. So essentially, what's happening? I have, so in the circuit model, a quantum computing or quantum computer was nothing but some inputs and some outputs and a unitary operator. So this is my U of f over here. And let's say, what does it do? So if I have an input state 0, 0, like 0 on this wire, 0 on this wire, uh, my output state is going to be 0 comma f0, because so this was my x bit, this was my y bit. So y plus f of x modulo addition is just going to give me f of 0 and 0. Now let's say on the same machine I have a unitary operator. I send this state in, a superposition of 0 and 1, and over here I send it 1. I send it 0. So what does this output give me? Well, now my output is going to be 0, f0 like before, in a superposition with 1, f of 1. It is still a modulo 0 addition, so it's just going to be like it's an addition y plus fx, so that's just going to be 0 plus f of 1. That's just going to give me f of 1 again. So over here. So that's going to be my state as an output. Okay. So now one of the homeworks for you guys is show that UF is indeed unitary. I'm claiming it's a unitary matrix. You just have to show it. Moving on. So how do I use the above circuit uh, for my task? And remember, my task was to find whether the given function f of x, by the way, this u of f depends upon the specific function f I want to determine. So Uh, I'm going to draw the circuit of the Deutsche algorithm. Here the input is. So let me call it. So again, as in circuits, this is the way time flows. Uh, this is psi1. Let me say that at this time, this is the state psi2 after coming out of the unitary gate, and this is my psi3 after I apply the Hadamard operator to the upper wire or the upper qubit. And again, u of f is evaluating nothing but this guy. Okay, so what is psi1? Psi1 is easy to write. Psi1 is just a tensor product of which is I'm just expanding it out. This guy. What happens to psi2? Now psi2 uh, is obtained after the application of the unitary gate. So psi2, if you look at it, I'm going to apply the unitary operator on this jazz. So I'm going to get 0 f0 for the first guy. I'm going to get 1 f1. Remember, this is the expression where y is this guy and x was this guy. Yeah, so I'm going to get 1 f1. Then what am I going to get? I'm going to get for this guy over here, I'm going to get 0 and this guy, and finally I'm going to get 1 this guy. Okay, so and of course I can normalize the state over here. So this is my state psi2. Let's look at psi2 more closely. Now let's take the first case. The first case is if I have a constant function. It's either 0 on both the values or it's 1 on both the values, doesn't matter. So notice, what does this evaluate to? My psi2 would evaluate to this guy, so instead of f0 on f1, I'm just interchanging. I'm just writing f1 0 because of this condition. So then I have 0. Binary addition with 1 flips it. So I can just write it as the complement of f0 minus 1, and I'll have again the complement of f0. When f1 is f0, doesn't matter if I'm taking the complement of one or the other. So this is my expression. What do I get after this? So what does it factorize to? So if you look at closely, let's do it on the next page. Okay, so this is what I have, and that would simplify to actually just taking it okay. So I'm just separating the term with 0, tensor product into f0 minus the complement of f0 and 1, so on, this way. So notice carefully, if f0 is 0, then f1, f0 complement is 1, so on and so forth. So what do I have? I have plus minus 0 plus 1 and f0 minus f0 bar. That's my state psi2 evaluates to. Similarly, so notice this is very important. This particular sign is very important. Just keep this in mind. What happens when I have a balance function? So case B, if this was case A, case B, if I have a balance function, then this is the condition that holds, and I'll just write it down explicitly. F0 bar then is equals to F1 in this case, and F1, the complement of F1 is F0. Okay. Okay, so if I have a balance function, I can again write down the same state. This was how I evaluated my psi2. Let's do it on the other page. Yeah. So sorry, this was a balance function now. So what does it evaluate to now? For a balance function, uh, this would evaluate to, let's say, I'm just going to write the factors. This is just algebra. Okay, so this is what we are getting. Essentially, we can write uh, this was our original expression, this was f1, and this was again f1. So we just replaced it by f0 bar, f0 bar. Is that correct? Yeah. No. So let me have a look at it. I apologize. This should not be the case there. Yeah. So let me just write the whole expression again. The most generic form of the state, which was psi 2 over here. So that's going to be this guy. Yeah. So this is the state again I am going to evaluate, and since now I have a balance function where f0 is not equals to f1, so what will that evaluate to? So I'll have psi 2, that's going to be f0, and I can again write it in forms of a factor. So I'll use the condition. So if f0 is 0, then f1 has to be, for example, 1, and vice versa. So essentially, that's the idea. So what I'll do is that I'm going to write it down. Let's say I can write it down everything in terms of f0 only. So f1 is nothing but f0 complement. And actually, I think what we were doing earlier was also correct. Doesn't matter. Yeah, so this would be again flipped up. This is going to be again f0, I think. So f1 will flip on binary addition from f0. That's going to become f0 only. Yeah. Okay, so that can be factorized, yeah, by 1 over root 2, which can be factorized as 0 if I take out f0 minus f0 complement, and I take out 1, that's going to be F0 complement this guy minus F0. Now I can massage it. I'll just take this minus sign outside, so that becomes minus which factorizes as this guy. So notice now I am getting a minus sign on the upper qubit. So when the function, so that's the beauty of it. Just stare at the upper qubit. I get this state when the function was balanced, and I got this state when the function was a constant. And these are orthogonal states. So all it boils down is to convert these states, and how do I extract this information? So this is the relative phase, -1. So extract, as a final step, extract the phase information using the Hadamard gate. So finally in that circuit I had, remember I had the Hadamard gate. This particular gate, Hadamard. What does it do? Well, it will give me, remember, either the upper qubit is this or the upper qubit is this guy, and depending upon this will give me 0 upon application of Hadamard if the function was a constant, or it's going to give me 1 if the function was balanced. So measuring the upper qubit, either a 0 or 1, I'm able to calculate whether the function is a constant or balanced. So noticed I used this black box or UF, whatever, this algorithm, I used it only one time. So there was only one input I sent across this computer, and I was able to retrieve my answer, which is terrific. For a classical computer, I'll have to do this process twice. So in a nutshell, we have evaluated a global property. Well, if a function is balanced or constant, it's a global property. A global property of fx using one evaluation. Well, this is in some sense twice as fast as a classical computer, right? So essentially, that's the idea. Let's say we were to, so in some sense you can argue that comparing a classical query to a quantum query are apples and oranges, that point is well taken. But let's say we were given, we could have the freedom of asking anything either to a classical computer, we ping it twice, F0 ping, F1 ping, and it gives us answers, and we are able to conclude using, uh, we do it two number of times, as compared to a quantum algorithm where we use this black box only once. We sent a superposition of states over here. We use this black box only once. Only once was this device used, and we are able to get into this register either the function is balanced or it's a constant. You might argue, well, this is a bit complicated. I used superpositions here, then I had this Hadamard, then I had to create this quantum gate, a unitary gate. Yeah, yeah, those points are well taken. But think about it this way: can we scale this thing up? Uh, so let's say fx is an n-bit Boolean function. So the input is going to be some string x2, xn. And we are given the promise that either it's a balanced function, f of x is balanced, or it is a constant. Now, well, roughly, if there are 2 to the power of n inputs, I'll have to do this calculation 2 to the power of n divided by 2 plus half. If it's a constant function, then I have to check it at least half plus 1 values, and all of these values, if they are same, I'll conclude it's a constant function. Right? Uh, but essentially, a quantum computer will give me this give me this evaluation, just one evaluation needed. I'll have a bigger circuit, but that sort of is the idea. Uh, that one evaluation on a quantum algorithm. So I hope now at least comparing it to a classical machine makes sense. Say in a classical machine, let's say n was 10 to the power of 8. Well, then you will have to make 10 to the power of 7 queries, order of 10 to the power of 7 queries to find whether the function is a constant or balanced. Whereas in a quantum computer, once you have set up the system, you just need to evaluate it only once, send it through a quantum circuit, and the upper qubit is going to give you the answer whether the function is constant or. So essentially, if you look at it, just if time is a crucial resource and you don't count the resources in constructing these guys, then essentially, yeah, as a proof of a principle, quantum algorithm is giving you an exponential advantage over a classical algorithm. So we'll see more of this in the next class, but this was an introduction to maybe a very artificial problem, but still in principle it shows that a quantum computer, at least in this query model of complexity, by query I mean how many times I'll have to ask the computer. So quantum computer requires exponentially less number of queries than a classical machine. Thank you.